All right. Before, in the previous section, we learned what an antiderivative was. And for example, recall that x squared is an antiderivative of 2x. And secondly, that so is x squared plus 7. Right, and x squared plus 10 will be, right? Because the derivative does not care about the 7 or the 10. It squashes both of them equally. So one might ask, is this always necessarily the case? Is this the only way for two different functions to be antiderivatives of the same function? And that is true. Let me write this as a fact. If functions capital F and capital G are both antiderivatives of F, then capital F minus capital G is constant. So two antiderivatives can only differ by a constant. How would we show this? Well, let's take a look at the derivative of f minus g. If the derivative of f minus g is then f prime minus g prime, but f prime and g prime are both f. So the derivative of f minus g is 0, and so the only functions with derivative 0 are constant functions. So this is indeed a true statement. Okay, so here's another definition. The indefinite integral of a function f is any antiderivative of f plus a general constant. We usually write something like this. The indefinite integral of f of x dx is some other function plus c. So let's write some examples of indefinite integrals. The indefinite integral of 10 dx is 10x plus c. The indefinite integral of k, a constant, dx is kx plus c. The indefinite integral of x dx. Well, what function has derivative x? Well, x squared, right? But derivative of x squared is 2x. So we put a 1/2 there. And then, of course, we also need plus a constant. The antiderivative of x squared is 1/3 x cubed plus a constant. Right? Now, in general, you might see a pattern here. When n is not -1, the antiderivative, the indefinite integral of x to the n dx, is x to the n plus 1 divided by n plus 1 plus a constant. You see that working in this example. Right, we see that right there. That seems to be holding. Now, why n not equal to 1? Well, of course, when n equals 1, we're looking at 1 over x dx. What function's derivative is 1 over x? Perhaps you recall, that's the natural log. So we have natural log of x plus a constant. Okay. Okay. Now, this seems like a good thing, but there's a little bit of a problem here. Is that this function, natural log of x, is not defined for negative x. Okay. When x is less than 0. But if we note the following thing, if x is less than 0, we can look at the natural log of negative x. That's a perfectly fine function. When I take that derivative, I get 1 over negative x, and then by the chain rule I multiply by negative 1. I get 1 over x. So I actually get the same function regardless. So the way we treat this is that we write the following. Instead of natural log of x plus a constant, we write natural log of the absolute value of x plus a constant. And that takes care of both cases. Let's record a few more examples. The indefinite integral of e to the x dx is e to the x plus a constant. The indefinite integral of cosine of x dx is sine of x plus a constant. The indefinite integral of sine x dx is negative cosine x plus a constant. And the indefinite integral of 1 over cosine squared x dx is tangent of x plus a constant. All right, now we can take these general rules and kind of do a little slightly more complicated versions of this. So let's take a look at some more complicated ones. We want the indefinite integral of e to the 3x plus 2 sine x dx. Now, the rules about derivatives say, or the rules about integration say that we can write this integral as a sum of two different integrals. And also, if you recall, constants, multiplicative constants, can be pulled out of an integral. So now we're left with things to understand. This is 3 e to the x plus a constant. This is 2 cosine x plus perhaps another constant. The constant doesn't matter, we just need to record it at the end. We really could write 3c, but we don't worry about that. We let this constant change value. All we want to do is make sure we have some constant at the end. It doesn't matter what it is. We don't want to forget it, though. In fact, WebWork might say something is wrong if you don't have the constant, so keep that in mind. Okay, let's take a look at another different, perhaps more difficult one. Maybe not difficult is the word, but more difficult. Let's take a look at the antiderivative of 8 over root x dx. Now, the key to these is to write them in exponential form, like that, where we have x to the minus 1/2 instead of dividing by x. This is square root. This allows us to use the formula from before, that we do n plus 1. So this is going to be x to the 1/2 divided by n plus 1, which is 1/2. Here n is equal to negative 1/2 from the formula that you wrote down above. Now when we figure this out here and write this carefully, this is 16 x to the 1/2 plus a constant. Constant should be here too. So this is 16 root x plus a constant. Okay. Let's look at some other situations here. Let's do a definite integral from 1 to 3 of dt over t. Okay. Well, the antiderivative is natural log of x plus a constant, but we don't actually need the constant. Let's carry on the constant. And the way that we use this notation here is we write this, right? This is the antiderivative, and these are the limits of integration. And then we plug in natural log of 3 plus a constant. Then we have to subtract what happens when we put in 1 into this. Now natural log of 3 is something. Natural log of 1 is 0. But look, we're adding the constant and subtracting the constant. For that purpose, often when you're doing definite integrals, you suppress the constant. It would be perfectly fine to write this, right? This is only when we have limits of integration that we can suppress the constant, because it's going to wash away. Okay, let's do one that needs a little bit of work before we can go anywhere with it. The antiderivative of 1 plus y squared over y. Now this looks pretty difficult. In fact, it looks almost like it's going to be a problem from Calculus 2. But if we just do a little bit of simplification, we get, this should be dy. 1 over y plus y is the same thing as 1 plus y squared, all divided by y. So this allows us to say, okay, 1 over y becomes the natural log of the absolute value of y. Y becomes 1/2 y squared. And then we need the additive constant tagged down at the end, no matter what. All right, so take a look at the worksheet and get some practice with this. This is, I hope for you, a much easier process than drawing the graphs was from the last section.